In this lecture, we'll learn about ceramics, bioceramics, and glasses. Earlier, we had learned about what are the kind of processing techniques we can utilize. In this particular lecture, we'll realize how we can really tap into a material in terms of putting it for a particular biomedical application. So once we know what kind of processing we're going to utilize, we can select a kind of material. It can be bio-inert, it can be biocompatible, it can be ceramic, it can be anything else. So how we can really tap that material, mostly ceramics and glasses, in terms of its application for a particular processing. So coming to the inert crystalline ceramics, so there are a couple of variety of crystalline materials which are inert in nature. So in this particular case, we can see that aluminum can be utilized as a material for basically for the load bearing applications such as hip prosthesis or dental implants, because it is highly inert in nature, and we can really see that it can impart high corrosion resistance to any entity. So once it is inserted into the body, once it is highly pure, more than 99.5%, it can serve as a load bearing implant basically for hip or dental implants. At the same time, it does not induce any toxic effects. So in that particular manner, it is also cytocompatible in nature. So that's what we can see in terms of cytocompatibility, that our aluminum oxide is highly cytocompatible. At the same time, aluminum oxide is being ceramic, it has highly wear resistant as well. So we can see that alumina, its hardness is 9 on the Mohs scale. So we can utilize ceramic, aluminum oxide ceramic for a high wear resistant application. So aluminum oxide is able to provide us high wear resistant, excellent cytocompatibility, and at the same time it has very high corrosion resistance. So it can be utilized as a scaffold material for the load bearing applications such as hip prosthesis or dental implants in that particular manner. But one more, there are certain conditions to it. So let us first talk about aluminum oxide, the inert material. So aluminum oxide has to be very fine grained, 3 to 10 microns, because it comes from the fact that if we have a very coarse grained aluminum oxide, and as soon as the two adjoining bodies they are basically undergoing contact with one another. So once the abrasion is occurring, all the grains will start removing off. So if grain size is very huge, say more than 100 microns or to that particular order, we will see the grains are coming off around the same order. So once the grains are very fine, it can impart much superior wear resistance to aluminum oxide. And to densify it, we add magnesium oxide, which is less than 0.5% as a sintering additive. And then sintering has to be done at very high temperatures, because melting point of aluminum oxide is to the order of more than 2000 degrees centigrade. So we need to do pressing and sintering at very high temperatures to the order of 1600 to 1700 degrees centigrade, and high densification also leads to very high compressive strength, which is to the order of 4.5 gigapascals. Since it's a ceramic, it has a very good compression strength, but not that good of a tensile strength. So and generally all these implants, they are under compression. So generally this aluminum oxide can show a very good compressive strength being ceramic. It has a bending strength of around 500 megapascals. And these are certain conditions which are imposed by the International Standards Organization, so that once we have a particular aluminum oxide, it should meet or exceed all those ISO standards or norms. So it also consists of some purity level. So if aluminum oxide has to be purer than 99.5% plus. So and apart from that, it should have a good compressive strength. It should have a good bending strength. It should also have a Young's modulus to the order of 390 gigapascals. And once it is meeting those standards, international standards, then it can also resist impact fatigue. And one more thing, what researchers have seen is that once we are increasing the grain size, say from 4 to 7 microns, so just increases from 4 microns to 7 micrometers, then it can decrease the mechanical properties by approximately 20%. So that is a deteriorating effect of increasing the grain size. So even if you are going from say 4 micrometer grain size to say around 7 or 8 micrometer grain size, we are expecting a deterioration of mechanical properties by approximately 20%. So once the grains are much more coarser, they will also impart poor wear resistance to the aluminum oxide. So that is the overall thing what we really can see. At the same time, we have to minimize the sintering aids. We are adding magnesium oxide as a sintering additive, so that we can achieve a sintering at a much lower temperature. And we need to minimize the sintering aid, because we also want to keep aluminum oxide as pure as possible. So that is the overall deal, that we want to keep minimize the sintering aid. At the same time, we should be able to achieve high mechanical properties, and also we want to maintain a lowest grain size that is possible, around less than 2 or around 3 to 4 microns. and then it should also have Young's modulus and some bending strength and compressive strength levels. So that is what overall idea about using the aluminum oxide. And it has been seen that the load bearing lifetime can be as high as 30 years at a load of around 12 kilonewton. So once we are designing an implant for a particular youngster, like once when very young patients are basically they undergo bone fracture or something like that, we need to design aluminum oxide. The sphericity of it should be very highly critical, because if it fails earlier, the person will have to undergo surgery for more than twice or thrice during their lifetime. So we need to see that the load bearing lifetime is approximately 30 years at a load of around 12 kilonewtons, but at the same time we need to make it much more cytocompatible while maintaining sphericity between the two contacting surfaces, to maintain the grade of aluminum oxide, that it has to be pure such and such mechanical strength in terms of its compression strength, fatigue strength, also maintain its grain size. So these are all certain extra additional features which need to be incorporated in terms of designing aluminum oxide, specifically in youngsters, so that they don't have to undergo surgery for more than once or twice during their lifetime. So that presents that aluminum oxide, it has excellent cytocompatibility that makes it inert. It can also allow cementless prosthesis fixation. So that is one more advantage with aluminum oxide, and also at the same time it can also show exceptionally good tribological properties, and COF can go from 0.1 to less than 0.02. So if we have two contacting surfaces such as metal and a polymer, that will tend to show much higher coefficient of friction, because polymer is very soft, metal is very strong. So basically once they are among the contacting surfaces, they tend to have very high coefficient of friction, whereas if we start using aluminum versus aluminum contact surface, it can reduce the coefficient of friction. At the same time, its wear rate will also get decreased. So that is the advantage of utilizing aluminum oxide as a contacting surface, both for ball as well as socket. So once they are in contact with one another, they will tend to have very low wear rate, and because they both are ceramics and they tend to have the similar chemistry, they will undergo very low wear rate, and it will be much coefficient of friction will also be much lesser than that of a metal versus polymer contact. So that is the overall deal with enhanced wear resistance of aluminum oxide. And specifically for aluminum ball and socket joint, it should also have a very high degree of sphericity. So that can be provided by polishing the surface, because we already know that once we have very high porosity of very high surface roughness, that will also tend to induce much more locking between the surfaces, the mating surfaces, and that can also induce very high coefficient of friction, and that will remove the smoothness which will come out at the surface level, because surface is the one which comes in contact first, and that decides what is the overall reaction or the kind of reactivity which is happening at the surface, and that will provide the smoothness with at which the two mating surface will interact. So once we have a very polished surface, we can get a very high degree of sphericity, and because of that we can also expect reduced coefficient of friction with time, and wear rate can be 10 times less as compared to that of a metal polymer mating surface, because they will have very high coefficient of friction, as well as one is polymer, one is metal. So metal will tend to eat away the polymer, it will start yielding the polymer because the drastic difference between their hardnesses. So once we have alumina versus alumina surface, they will have a very low coefficient of friction, and that will also have very low wear rate, which is approximately 10 times less than that of a metal polymer surface. And again we can also do press fitting of alumina on the non-cemented cup. So that is that's what leads us to the cementless fixation of the particular implant. So we can also achieve the non-cemented cups into the acetabulum of the hip. So we can get the particular joint of the acetabular cup with the ball. So we can get that without any cement fixation. And again the cups, they get stabilized with time by the bone ingrowth. So we have certain pegs into which this basically the bone will start growing, and that's how it will secure the cup. So we can see that we can have a very nice way of engineering this particular cup, alumina cup, that we have a cup and all the pegs, they are being inserted with bone ingrowth, and that's how the cup is basically stabilized to later on it has a press fitted kind of a sphere or a ball, which takes care of the overall stability of the overall joint. And again the femoral ball is basically bonded to the metallic stem. So we have a particular ball, and then we have a femoral stem which basically joins it, and then we have acetabular cup, and that thing is basically fixed with the bone ingrowth, and this is a stem, and over that ball is again made up of aluminum oxide, Al2O3 ceramic, and this can also be Al2O3. So in that manner we can achieve alumina versus alumina interface out here at this location, and that will provide a very low coefficient of friction, and it will have very low wear rate as well. And again, there can be one problem with utilizing aluminum oxide is that it can result the bone entropy, because once the modulus is very high, once the wear rate is very low, and then the nearby bone, the nearby cancellous bone will start basically thinking that, oh, I am not needed because the load is being borne by aluminum oxide itself, so I am not needed. So it might lead to cancellous bone atrophy once we have aluminum oxide ceramic as well, and because it has very high Young's modulus and bending strength and compression strength, so the bone may start thinking, oh, I am not required here at all because the load is totally being borne by aluminum oxide. So that is one problem which can lead to the bone atrophy, and it can thereby lead to the loosening of the acetabular cup, specifically in the old patients. So that is one problem which we can face with aluminum oxide. So that part needs to be counteracted with a certain mechanism. But the overall philosophy of using aluminum oxide is because we can maintain very high sphericity, so it can lead to a very smooth surface, and once it is a very smooth surface, again it's alumina to alumina contact, that will reduce the coefficient of friction, and the wear rate will decrease approximately 10 times as compared to that of a metal polymer joint. And but the only and the cup part gets stabilized by the bone ingrowth along the cup area, and the ball is basically being bonded to the metallic stem part, femoral stem. And then the problem with aluminum oxide is it can lead to the bone atrophy, the cancellous bone atrophy, and that might lead to the loosening of the acetabular cup, specifically in the old patients. So that might result with the utilization of aluminum oxide. And the second inert material is zirconia. So zirconia is also used as a ball in the hip prosthesis, and the advantage of zirconia is that it has a lower E value or the lower Young's modulus, but it has a higher strength. And zirconia has been used very recently. It has been very less time, so there is not sufficient data clinically which is available to state whether zirconia is highly successful or not. So because there have been less than 15 years of data which is available for zirconia, so people don't really know about what will happen if zirconia is being used. But it appears to be a very promising material to be used as a ball in the hip prosthesis, because it has very high pressure toughness as compared to that of alumina. At the same time, it has low modulus as compared to that of alumina. So it can provide a better compatibility with bone. And the only problem is it does not have sufficient data so that we can clinically say that, oh, it is so and so, and then we should be able to start using it. So that is still missing in the research part, and that has to be taken care. And second part, apart from the inert materials, second thing is porous ceramics. And we learnt about how porous ceramics can really assist the cells to basically get in, and they can really anchor themselves through the porous region, and they can extend up to around 100 microns as well into the implant material. So they basically allow inertness plus some mechanical stability. So that is what can be achieved from the porous ceramic. But once the ceramic is getting porous and porous, they can't provide the load bearing, because if I have a solid material, it can provide me certain load bearing part. But once I start having some porosity into the material, then obviously the overall modulus or the overall strength of the material goes down drastically. And if porous size is and pore size, sometimes they are required in excess of 100 microns, so that cells can really come and they can attach themselves or get in contact. So basically implant it should have a structural bridge for the bone formation. So basically the implant should have some structural bridges of the porosity so that bone can really grow and it can form out there. And those porosity can be induced in that manner that we have certain corals, and there are certain porites or goniopora, and they already have interconnected porosity, which is the order of 140 to 160 microns, or in goniopora the pore size can be as high as 200 to 1000 micrometers. So if we can somehow convert that the calcium carbonate part to hydroxyapatite via some hydration technique, we can get hydroxyapatite which is totally porous. So that is how we can engineer that. We can utilize certain corals which already have some porosity in them, and then we can somehow convert that calcium carbonate upon hydration to hydroxyapatite in terms of tapping the advantage of that particular thing. So we can see that we can porous ceramics are highly important, and they are well known for their inertness, and they can also provide mechanical stability, so cells can really grow into them. But the problem with them is they can't provide load bearing capacity, so they have to be used as a coating. That is the key part out here, that once we have porous ceramic, we can utilize them for as coatings, and the coating for the coating, the pore size has to be approximately greater than 100 microns, so that cells can grow, they can extend, and they can get mechanically interlocked, and that can provide a structural bridge for the bone formation, because bone has to start growing, it should get interconnected, and that can be attained either via creating certain porosity into the material, or we can utilize certain corals which are calcium carbonate, and they already have interconnected porosity, and we can convert that particular calcium carbonate via some hydration technique to hydroxyapatite to be utilized as porous materials. And porous ceramics, they are highly potent bone implants, and first of all we can utilize calcium oxide that can form an investment material to form porous material. So we can have some calcium oxide phase, and that will serve as a scaffold, and then we can easily dissolve that CO structure in HCl, and basically now we can control the porosity size, we can control the porosity shape. So we can mix calcium oxide with some material, another material or another ceramic as a combination, and the size of calcium oxide will decide what is the kind of porosity, how well connected it is, what is the size of porosity, how the pores are being distributed. Those all things we can control with calcium oxide, and then calcium oxide can be dissolved via HCl or the hydrochloric acid, and now what is remaining is a overall structure which is highly porous. And also certain other materials such as titanium oxide or alumina or cobalt chromium or silicon rubber or calcium phosphates or polymethyl methacrylate, there are certain materials which have been used as a bone implant already, but among them calcium phosphate is being the most acceptable, because it has chemical basically it's nothing but a structure of what our bone has, combination of calcium and phosphorus. And again one more problem with this particular material is that once we have some porosity, that is basically reducing the strength, and that decreasing strength should be matched by the bone ingrowth of the implant. So once we have certain material which has certain porosity, and soon we will see that because of the porosity there is much degradation or much more wear of the porous region. So once this particular part is getting degraded, we should also have that bone which is basically the implant material which is getting degraded, that thing is being captured by or being replaced by bone ingrowth. So once we have bone ingrowth happening at the region where we are seeing a deterioration of the implant material, that is basically balancing it. So we have porous material that has once it is highly porous, it has very low strength, so it will undergo much more wear or much more degradation. So as soon as it is getting degraded, the new cells which are forming, they should start or replacing the damaged material. So that's how it can really balance, so that overall strength can be provided by the new bone cells which are forming at that particular location, and that's how the overall porous material, how they can really benefit the formation of a new bone or new bone cells out there. And one more way of classifying the material is, apart from we had the porous materials, or we also had the inert materials, there is another class called bioactive glass. And these certain glasses or ceramics or glass ceramics, various classes of this bioactive glass, they can form bond with the bone, and there are some special bioactive glasses which can even bond to soft tissues. So we have our hard tissues, and we also have soft tissues, so we can have even some bioactive glasses which are highly special, so they can bond to even soft tissues. And again the phenomena is time dependent, and also needs certain kinetic modification of those particular material, so that it can so that the surface can form carbonated hydroxyapatite layer, which is highly compatible to the bone, to the cells which are the bone cells which are growing, and at the same time they result adherent interfaces, and that once the surface is highly adherent, then its strength or the cohesive strength can increase that of a implant material. So that is the overall strategy about it, that we have certain glasses, ceramics or glass ceramics, they can basically bond to hard tissues or soft tissues, and again we can induce certain time dependent factors of how it is getting dissolved and how a new cell is taking place of it. We can also modify the surface. At the same time, we can also induce some bonding between the material and the cells, and the bonding is so strong that it is much higher, the addition, the interface strength is much higher than that of a implant material itself. So that can basically allow the cells to keep remaining there, and they will keep bonded to the implant material. And this particular type of activity was first shown in bioglasses, and that bioglass is a combination of silica, which is less than 60%, typically 55% is being utilized, high sodium oxide and calcium oxide. At the same time, we have to maintain high calcium oxide by P2O5 ratio, and this particular material induces some surface reactivity once it is put in aqueous media. So that is what our feature is. We take this material, put it into the body, and once it is in getting exposed to some liquid media or aqueous media, it starts hydrating it, and that's how it will result some bonding with the bone. So this is how the combination of silica, calcium oxide and sodium oxide is available, that we obtain certain regions, certain combination of this silica, around 60% of silica and some combination of CaO and Na2O to result a bioactive region, and certain region which is higher in silica, it is highly inert because of formation of silicon oxide, and again a certain content of Na2O can also make it resorbable. So we can have certain material which can get resorbed into the body, and that's what we really looked earlier as well, that the material which is going to be resorbed into the body, it should also be compatible, because if I have some toxic material and it is getting resorbed, it should also be compatible with the body. So the parts which are breaking off, they should also have much more compatibility while they are breaking off. So this is overall combination, and this particular combination is not possible, calcium oxide versus Na2O. So that is what not practical purpose. So we have silica, certain combination of silica to and some sort of combination of calcium oxide and Na2O to result a bioactive region, and we can also achieve a resorbable region. We can also achieve a nearly inert region via particular combination of silica, calcium oxide, P2O5 as such out here. And there is one so apart from that, we can the bonding of with the bone can also happen in certain stages. Like in stage 1, we have in the glasses we have alkali extraction from the glasses. Once a particular material is exposed to some solution, so in this from a solution we can generate some hydrogen ions, and that hydrogen ions can combine with alkali ions which are present in the glasses. So we have some alkali ions, they can they can combine with the hydrogen, so that will lead to the alkali extraction from the glasses, because they will combine with hydrogen to form certain bonding with them. So that is what will happen in the first stage, that alkali will start getting dissolved, it will start forming basically combination with hydrogen ion, and that's how it will remove the alkali ions from the glass. And second, once the alkali ion is basically removed, it will break the silica structure. So all the network we had which was present in the silica because of the alkali ion, that will start deteriorating the silica structure, and it will break it, and basically the glass will start dissolving at the interface. So once we have a solution, once we have a glass, the alkali will start getting trapped by the hydrogen ions, and once we have hydrogen ions, it will start dissolving the glass, because now there is no more alkali ion that is deteriorating or breaking the silica structure. Once silica structure is broken, glass will start dissolving at the interface. So that is the second stage. And in the third stage, what we see, that silica starts repolymerizing on the glass surface, and that occurs via the condensation of silicon or OH ions, silicon SiOH ions, that is nothing but silanol. So again silica starts getting polymerized on the glass surface, and from that we start seeing precipitation of calcium phosphate on the silica rich layer, and again with the presence of aqueous medium, we also see crystallization of carbonated hydroxyapatite. So that's what we are able to see, that once the silica oxide is dissolved, it gets repolymerized via condensation, and then we see a generation of CaP amorphous layer on the silica rich layer, and that basically leads to the crystallization of calcium phosphate to form a carbonated hydroxyapatite. So from amorphous CaP we come back to the carbonate HA, and again here also we need to basically match the mineralization rate so that it matches with the absorption kinetics, because as soon as the absorption is occurring, so that has to be matched with the how carbonate hydroxyapatite is forming. So absorption of this particular phase or the breaking up of the glass and that thing has to be matched with the mineralization of how carbonated hydroxyapatite is forming on the surface. And basically what will happen if we have a rapid rate of dissolution of glass, obviously we will have higher bioresorption. So overall process is like this, we are seeing deterioration of glass on the surface, and that is being matched by the crystallization of hydroxyapatite on the surface, carbonated hydroxyapatite. So if you have dissolution occurring at much rapid rate, it will overall damage the structure. So the structure won't be able to sustain any load, and overall the integrity at this interface also will go bad. So we need to see that at the rate at which the glass is getting resorbed, the same rate we should generate the kinetics that hydroxyapatite, the carbonated hydroxyapatite should start getting precipitated on the silica surface. So that's how they should both should match and result a bonding with the bone. So that's what we are able to see for the bioactive glasses. And again, the bioactive nature of the glass, it can bond with bond, but it has been observed that small additions of alumina, even less than 3%, or tantalum oxide, titanium oxide, antimony and zirconia, they inhibit bone bonding. So even small additions of them, they serve as so strong oxides that it doesn't lead to the bone bonding, because there is no more silica available on the surface, and it doesn't lead to the bonding with the nearby tissues. And again, once we have very high surface silica or any oxide will form a protecting glass film. So once we have something protecting on the surface, they basically are not compatible with the they don't want to form a bond with anything else. So we have inert layer, and that doesn't lead to any bond formation with the cells on the surface. So what happens once you have porous silicon oxide layer, that will lead to the alkali ion exchange. So once the layer is enough porous silica, that can form basically that can lead to alkali ion exchange with the solution which was present earlier. But again, some static conditions, they can make pH alkaline, and then that can dissolve the silica layer. Our silica layer is acidic in nature, so any alkaline layer will start basically dissolving it. So it can happen the other way as well, that once we can make pH more acidic, it will lead to less dissolution of silica oxide, SiO2. So that is one more problem with that. So we need to have some conditions which can make pH more alkaline, and that will start dissolving this SiO2 layer. And once SiO2 layer is much more porous, we can lead to alkali ion exchange, and that is basically nothing but the degradation of the glass, and that will basically lead to the bonding of the implant with the new bone. And it can be either morphological fixation, or it can also be biological fixation, or it can also be bioactive fixation. So once it is only morphological, only surface related, we can have very poor interfacial bonding. Biological fixation, we can have better interfacial bonding. But once we have bioactive fixation, it is similar to the healed cortical bone. So basically the healing is much more assisted by the bioactive fixation, because morphological we only have kind of a mechanical bonding. In biological fixation we have much more porosity which is assisting, but in bioactive fixation we also have cells or the surface which is getting degraded. At the same time, it has very nice bonding with the newly growing cells. So that is what is basically initiating the bioactive fixation. It will be very nice that because we are getting a kind of a structure which is similar to that of a healed cortical bone. And again, the thickness of this bioactive fixation, it is very low, because this low thickness can lead to high shear strength. But if we have very high thicknesses such as 200 micrometers, they can result very low shear strength. So in bioactive fixation we have very low thicknesses of the bonding layer which forms, so it can take very high shears. So that is the advantage with the bioactive glass with a very less interfacial thickness. So we can see that we have small layers, small additions of the alumina, tantalum oxide or zirconia. They tend to form very high, a very thick oxide layer, and that basically inhibits the bone bonding. And once we have very dense silica, again it will also lead to the inhibition of any bone bonding, because it has a very protective layer on its surface. So once we have a very thick layer, it won't lead to any alkali exchange. So for that we need to have certain porosity associated with it, or it can also be by increasing the pH or having an alkaline pH, so that we can eat away the silica and it should leave certain porosity, and then we can achieve the alkaline exchange, and that will basically break the glass. And now once we have broken the glass, it is nothing but resorption, and that thing will lead to the bioactive fixation. And bioactive fixation, we have kind of a balance between the material which is going off and the balance with the, and it is balancing with the kind of new material which is going on its surface. And since it is getting degraded, the cells find it very comfortable to get attached to the bioglass, and then it also forms a very thin layer, interlayer, which is around 20 microns, and it has a very high shear strength, and that basically leads to very good bonding between the material which is getting degraded, that is the bioactive glass, and then the bone part, the newly growing bone. And the bioactive part, we also have something called the bioactive material. We also have calcium phosphate ceramics, and again calcium phosphate has been utilized in dental implants, periodontal treatments, orthopedics, maxillofacial surgeries, and all that. Again, at more than 4.2 pH, we see that hydroxyapatite, which is Ca10 PO4 OH twice is stable. At less than 4.2, we have brushite. It is called Ca2P or CaHPO4 2H2O is stable. Or at high temperature, we have beta tricalcium phosphate, is called Ca3 PO4 whole twice is much more stable. And again, at high temperature, we also have tetracalcium phosphate, which is Ca4 P2O9, which is stable at very high temperatures. So we can see calcium phosphate has been utilized basically for dental implants or maxillofacial surgery or periodontal treatments, and at more than pH of 4.2, so for more alkaline thing, we have hydroxyapatite, which is more stable. So once we are able to create some static conditions where we can generate some alkaline pH regions, we will find that hydroxyapatite will start precipitating. So for that we need to have pH of greater than 4.2, and but at pH lower than 4.2, we have brushite, that is C2P, or this particular structure is stable. But at higher temperatures, we have tricalcium phosphate and tetracalcium phosphate, which are much more stable. So we can see that earlier we had seen that we can also form hydroxyapatite. So we can take even porous corals, and then we can basically try hydrating it to form hydroxyapatite. So we can see that unhydrated calcium phosphate, it can interact with water or maybe body fluid even at body temperature to form hydroxyapatite. We can see some tricalcium phosphate is interacting with water and is hydrating into calcium phosphate plus some ions of CaNHPO4 2 minus. And as we saw earlier, that the solubility of tricalcium phosphate decreases with pH, and which can further decrease the solubility formation of TCP. So we have certain ions which are getting generated. So once we are decreasing the pH, it will start reducing the solubility of TCP. So we want to make it much more alkaline, so that if we want TCP to dissolve into the body, we should we should generate the condition in which the nature is much more alkaline, and that will lead to the more solubility of tricalcium phosphate. And also porosity can also increase the solubility of TCP, because there are more number of interaction sites which can interact with TCP in terms of breaking it down. So we are seeing that tricalcium phosphate, it's interacting with water to form hydroxyapatite, and that is nothing but the dissolution of or the solubility of TCP. Again, to form a calcium phosphate, we need to sinter it at very high temperatures, approximately 1000 degree to 1500 degree centigrade, and then they are compacted into a desired shape. And again, the water which is combining with it, it is stable up to even 1360 degrees centigrade. So basically, one more problem with the calcium phosphate is that it is very difficult to predict the high temperature phase and what will be the content, because we have tricalcium phosphate, we have tetracalcium phosphate, so we don't know what will be their stability part as well once they are being cooled to the room temperature. And because it is also combining with water, so so the overall composition or overall phase which is forming at the room temperature after cooling, it depends either on the partial pressure of water, which is stable up to 1360, and again what is its partial pressure, what is the approximate cooling rate, and at the same time what are the kinetic barriers which are leading to the formation of hydroxyapatite. So those are certain criteria which needs to be really realized. So it becomes very difficult to predict what will be the overall phase once the particular material is cooled to the room temperature. Because calcium phosphate, it has to be sintered at 1000 degree to 1500 degree centigrade, and once it has to be compacted, it has to be cooled down, and again water is much more stable even up to 1360 degree centigrade. and to make the material we need to cool it down back to the room temperature, and depending on its kinetics, depending on the cooling rate, depending on the partial pressure of water, it becomes highly difficult to predict what kind of phases will form and what will be the distribution finally. And at the same time, we can see the porosity also have very drastic effects on the material properties. Generally, microporosity, it is less than 1 micron, and that results from the incomplete sintering. So that is the part we once we are sintering it, we don't want any microporosity, so that will make the material very weak. But at the same time, we are requiring macroporosity, which is more than 100 micrometer in diameter. Why? Because cells can really grow and they can get entrapped and they can anchor themselves to the implant material. So that will assist in terms of the bone growth. But once we have macroporosity, it also deteriorates the mechanical properties. So we can see that the total porosity that is given by the VP part. So we have the total porosity of VP, that is basically degrading the compressive strength. So whatever compressive strength we have, that is getting degraded by the total porosity. So it is being degraded by the porosity because this term is negative. So as VP increases, our sigma c will start decreasing to a large extent because the dependence is exponential. So that is the overall deal with it, that higher the porosity, the compressive strength will decrease exponentially. So that is the basic problem with it. But once it comes to the tensile strength, it depends more on the microporosity, and the tensile strength will again decrease exponentially with as soon as the microporosity starts. Vm is the microporosity. As it increases, our sigma t or the tensile strength will decrease very drastically, because although microporosity can serve as a potential crack initiating site. So as soon as we have some tensile stress, the propensity to form much more cracking is highly increased once we have microporosity, because those are the regions which will serve as stress intensity factors of increase of stress intensity factor, and that can lead to crack formation. So that will overall lead to the lower reliability of hydroxyapatite under the tensile loading. So that is a problem with the porosity part. We want the porosity, but at the same time it is very damaging mechanically. So biologically we want porosity, but mechanically it is not suited because it will decrease the tensile strength or even the compressive strength. Compressive strength depends more on the total porosity, whereas tensile strength more depends on the microporosity, because that is much more potential site for forming new cracks. So we can so that eventually leads to the lower reliability of hydroxyapatite under the tensile loading. So ideally calcium phosphate, they have been used in the clinical practices. They can be used as powders, or they can be utilized as unloaded implants, that is unloaded implants such as in ears, because there we don't require any load, or they can also be utilized with reinforcement of metals such as in dental implants. So we have dental implants or we have unloaded implants, and essentially they can also be used in the coatings, because once we have calcium phosphate we wanted to degrade, we can apply them as coatings, because as soon as the new cells they are forming, they will start taking place of the older material or the bioactive material, and that's how they will get resorbed. Calcium phosphate will get resorbed, and then it can serve as a very nice coating. And they can be also used as a low loaded porous implants. So bone itself will act as a reinforcement. So those are the several uses of the calcium phosphate, that they can be utilized as either as powders or unloaded implants, or with reinforcement or with the metals or coatings, or low loaded porous implants where the bone itself will act as a reinforcement of these particular materials. And again, what happens in the bonding of with the hydroxyapatite implants is that cellular bone matrix it starts generating, and it generates by the differentiation of the osteoblast, and it forms a amorphous band between the cellular bone matrix, and it has certain amorphous layer which generates. So between the amorphous and the bone implant region, we have certain cells and collagens and bone minerals that start developing in this particular interface. So we have certain region between amorphous and the cellular bone matrix. So that particular region starts developing some cells, collagen and bone minerals, and then it starts shrinking the bonding zone, and this bonding zone shrinks down to the around 0.2 micrometer. So we have all the cells, collagen, bone mineral, they start developing, they start pulling those things together, and that basically leads to the bonding zone shrinking to less than 0.2 micrometers, and normal bone will start then attaching itself via thin epitaxial bonding, and it will have some aligned hydroxyapatite or the apatite crystals which are nicely aligned in the natural bone, and that alignment basically leads to the high gradient in the elastic modulus. So in one direction where we have all the apatite crystals aligned, we get very high modulus, and that's the reason it will have very poor modulus in the perpendicular direction. So overall we can see hydroxyapatite, we can see that cellular bone matrix will generate once the osteoblasts are differentiating. It forms certain amorphous region, and in that particular in the particular region between amorphous and this particular interface, we have cells, collagen and bone minerals. They start to develop, and because of that it start shrinking to less than 0.2 microns, and now that brings the bone closer, and it basically starts forming epitaxial bonding, which are nothing but the aligned apatite crystals, to lead to a very high Young's elastic modulus. Again, the resorbable calcium phosphate, we saw that it depends on the pH. So as soon as pH is much higher, we start much more solubility, start seeing much more solubility of calcium phosphate. So it also depends on the pH or the solubility product, and it can also have amorphous calcium phosphate, dicalcium phosphate, or even octacalcium phosphate, and it can also be a physical disintegration, because what happens is there are small particles, they get attacked chemically, and those particular chemical activity occurs more at the grain boundary. So these small particles, they basically result because of chemical attack, and those particular particles, they start going at the grain boundaries or anywhere else, and they start disintegrating the material physically. And there can also be some biological factors. So we have either dependence on the pH or deterioration from the powder particles or the debris particles. There can also be some biological factors such as phagocytosis that causes a local decrease in the pH, and again it also depends on the kind of material which is present, such as degradation of alpha TCP is much more than degradation of beta TCP, which is even higher than that of a hydroxyapatite. So the resorption of the bioactive calcium phosphate depends either on pH or the solubility products which are present out there, and generation of particles can also lead to the mechanical degradation of the calcium phosphate. There can also be some biological factors such as phagocytosis can also cause a local decrease in the pH, and that will basically reduce the solubility of tricalcium phosphate. Or again at the same time, if you have more of TCP, alpha TCP, beta TCP, then they have much more degradation than that of a pure hydroxyapatite. So those are also certain concerns. And again this biodegradation, it increases with increase in the surface area, because more the surface area, more there is interaction of this particular material with the surrounding environment, and there is much more loss either in terms of corrosion, in terms of particle interaction, or in terms of even contact with the nearby flowing media. Or it can also, biodegradation can also increase with decreased crystallinity, because once we have crystallinity, there are much more crystalline regions which can serve as a strong reinforcing regions. So once we have lower crystallinity, that can also lead to the degradation of the material. Again, once we have decrease in the crystal and the grain size, that can also lead to the biodegradation. And again, once we have ionic substitution of magnesium 2 plus or CO3 plus etc. in the hydroxyapatite, that can also lead to the biodegradation. That is nothing but the breaking of the glass, and then but that part basically combines with the hydroxyapatite, and basically it starts increasing the degradation of hydroxyapatite, because it can leach away the ions from hydroxyapatite and it can go away as something else. So what all we can do is we can stabilize OH in the hydroxyapatite via some fluoride substitution, fluoride ion substitution. It can also be induced in hydroxyapatite, that will lead to the increase in the or decrease in the biodegradation. We can also allow magnesium 2 plus substitution in the beta tricalcium phosphate for reducing its biodegradation, or we can also have lower beta TCP ratio by HA ratio, because beta TCP has much higher degradation rate. So once we start increasing the hydroxyapatite content, that will overall reduce the biodegradation. So there are certain concerns with increasing the surface area, or once we have ionic substitution of magnesium 2 plus or CO3 2 minus in hydroxyapatite, that is nothing but taking the ions away from the hydroxyapatite, so that leads to a very high biodegradation. Also, once we have a lower crystallinity, we don't have enough good of crystal sites to lead to stabilize the particular structure, so that we can avoid by inducing much more of F minus or Mg2 plus substitution in TCP, or even having higher hydroxyapatite ratio. So overall we can see that we have certain materials which can be highly inert, such as aluminum oxide or zirconia. So aluminum oxide has shown to be a very nice material because it has very high wear resistance, fracture strength, compression strength. At the same time, it has very low wear resistance, very low wear of the material. So in that particular manner, aluminum oxide is very good. Then comes to the overall material which can be highly active or they can be highly porous, and those, because of porosity, it can also start reducing the mechanical properties. So porous materials are generally utilized as coatings in the body implant materials. And later on we also have something called bioactive materials, and they can start forming bond with the particular newly growing cells, and that happens that we have to have a particular combination of silica, Na2O, and either also CaO. So that overall combination leads to a very good bioactive material, and that happens that we have breakage of the alkali metals with the hydrogen ion, and then we have redeposition of silica on that, and then over that we have mineralization of hydroxyapatite, and that leads to the overall bonding, and that bonding leads to a very fine film, and that has very high shear strength because it is approximately 20 microns, and that is how it leads to much more stronger bonding with the bone. Then we also have resorbable calcium phosphate, and that depends directly on the pH or the overall chemical composition. In case we have tricalcium phosphate, that can resolve at much faster extent. So we can also see how the pH and how the solubility or how the physical factors or the biological factors can induce the dissolution of this calcium phosphate, and so eventually we can choose a particular material which is according to our needs in terms of having a very good property. It can be bioactive, it can be bioresorbable property, it can be an inert property or inert material property. So how we can design it in terms of achieving a implant material which is very high life, at the same time it can serve the purpose with enhanced cytocompatibility. Thank you.